So 2.8 is basically talking about the related rate type of problem. So what is a related rate type of problems? Okay, so let's take a look at on the first example, and I'm gonna explain it to you what we are, which directions are we going. So in the problem, it say that assume that the oil spill from the eruptic tank spread it in a circular pattern whose radius increases at a constant rate of 2 feet per second. How fast the area of the spilling increasing, right? Spill increasing when the radius of a spill is 60 feet. So that basically talking about, here's a well spill, okay? And what happened is, the giving part is right here. The radius is increasing at the rate of 2 feet per second. And what they want is they want to know how fast this green circular pattern is increasing, right? At what rate is increasing, meaning how fast the area is expanding and out. So try to find out this type of rates of change on the area by itself. Sometime, this problem is not that difficult enough. In some problem, it will be more difficult to find by itself. So the idea of the related rate is basically we are looking for the rate of change of a certain things in terms of another rate of change, something that we already know. Okay, so that's the whole idea of this rate of change, because as we know that as this radius is increasing, at the same time the area will be increasing also, right? Because the radius and area, we do know that there is a relation between those two. So the whole idea of this related rates basically is using the rate of change of one quantity, right, in terms of another rate of change in a different quantity, something that we already know, so that we can compute it easier. So that's the idea of this related rate. Now, looking at this problem, first we can sort of see that, the picture. So whenever you can draw the picture, try to draw it. That will help you to label things, right? And at the same time, it's like making sure that you label it correctly. So at this point, the radius is basically the variable, okay? And we know that this radius will be increasing as the time, times go on. And as well as the area will be increasing also as the spill time is going increasing. So what we're going to do is this rate of change 2 feet per second for the radius part, that is basically talking about, okay, dr dt, which is equal to 2 feet per second. So the rate of change in the radius respect to the time, right? So that is basically like how fast the radius is increasing. That is a known value that's given to us. Now, what we want to find out is we want to find out how fast the area is changing. So another way of saying is this is basically the derivative of the area respect to the time. So what is the rate of change in area respect to the time? How fast that is increasing. That's what we want to know, question mark. And a lot of times this will only give you, right, the rate of change in area respect to time. There will be a lot of like value that comes out depending on, what is your radius is. Because at radius is one feet, then the rate of change in the area is different than, okay, when the radius is 2 feet or 3 feet or 4 feet, so on and so forth. So therefore, in the question, it specifically say that, right, we want to find out the rate of change, right, how fast the area is increasing when the radius is 60 feet. So to make sure you write it correctly for a later purpose, because the rate of change in area respect to the time, we want exactly at when the radius is 60 feet. And that's what we want to evaluate, okay, in this problem. So is there any other questions? So How can I, now the question is, how can I relate the radius and the area? That will come up with the formula that we know, the area of a circle, because it's talking about circular pattern. So area of a circle is equal to pi r square. So now, by taking derivatives on both sides with respect to the time, I will get, on the left-hand side, I will have the rate of change of the area respect to the time. And on the right-hand side of the equations, I will have the rate of change of the radius respect to the time. Right? So let's do that. So taking derivative respect to the time of the area, and pi r square. So this will give me derivative respect to time of the area that is equal to, since pi is a constant, I can basically take it out and then taking derivative of r squared, this will give me 2r. And remember, r is a function of time, so therefore we need to use the chain rule, which is times with dr dt. Okay. So remember that, in this case, area is respecting to time and the radius is also respecting to the time. So the radius is a function of time and area is a function of time. So that's why when we take derivative of r squared, we need to use what? The chain rule, which is the implicit differentiations idea that we learned in 2.6. So finally, if I simplify a little bit, that would look like derivative of a respect to t, which is equal to 2 pi r times dr dt. So what are we interested in? We are interested in looking for the rate of change in the area respect to the time for, not in general, for a specific radius. Right? So this is basically a general formula now that we got. So now we want a specific evaluation. So that will be the derivative of a respect to the time, which is going to be what? R equal to 60 at a specific radius. So this will give me 2 times pi times 60 times width. And we already know that this rate of change on the radius, which is a given, which is 2 feet per second. So when I multiply everything out, this will become 240 pi, right? And since this is the rate of change in area, that will become feet squared per second. And finally, the interpretations, what the question is asking you is how fast it is increasing on the area. So now I can interpret it that area is increasing at 240 feet squared per second, okay? When, right, this rate of change is at the particular length of radius, so you need to indicate that. So when the radius is 60 feet. And that will be my conclusions. Now, any other questions? So for the second problem, a camera is mounted at a point of 3,000 feet from the base of a rocket launching pad. If the rocket is rising vertically at 800 feet per second, when it is 400 feet up, and how fast, right, must the camera elevations of angle change at the instant to keep the rocket is in sight? So notice that in this problem, right, we have a launching pad. The rocket is, we have a launching pad and the rocket is going up vertically, right? And there is a camera that's putting on the ground, like, it's like looking at the rocket, right? And notice that this, I should draw a little bit bigger right here so that you can see the angle of elevations. So this camera is like, starting from here and then move up, like, as the rocket is moving. So what we know from here is this camera is 3,000 feet away from the rocket. So that number is never changed. Is from this launching pad to this, camera is always going to be horizontally 3,000 feet away. So that's what I'm talking about earlier. This is a fixed number so that I can write it down a numerical value in my picture. Then the next thing information is given to you is this rocket is rising vertically, right? Rising vertically at what? 800 feet per second. So you have to be careful right here because the rocket is not going at the constant rate, okay? Not everywhere is going 800 feet per second, because if you read it carefully, this one is saying that the rocket is vertically, rising 800 feet per second when it is what? 4,000 feet up. So that means this rate of change is at this height, instantaneous rate of change at this height. Okay. So that basically tells me the height right here, it will be always changing. Right? It could be like 1,000, 2,000, 3,000, so on and so forth. It could be always changing. So that's why I'm going to put a variable right there to represent it. And what we know is this, the rate of change on the height respect to the time when the height is 4,000 feet, okay? And we know that this rate of change is what? 800 feet per second. Now, the question is asking you how fast the camera elevations of angle must be changing to keep the rocket in sight at that moment. So the question is asking angles of elevation. So I can basically, like, look at this as a triangle, and angle of elevations, which is this angle that we are talking about. So in this case, we want to know what is d theta dt, what is the rate of change in angle of elevations respect to the time when the height is 4,000 feet at that instance. So is there any questions regarding this question so far? So now what we're going to do is to relate this to the rate of change in height respect to the time with the rate of change in angle respect to the time. We're going to use the functions tangents, because tangent theta, that is equal to opposite over adjacent, which is 3,000. So we can put a solid number right there. So now if I take the derivative on both sides, okay, so derivative respect to the time on the left hand side and derivative respect to the time on the right hand side. So we can look at it as 1 over 3,000 times with derivative respect to the time of the h, right? That's the same meaning. And remember, in this case, h is a function of time and theta is a function of time. So when I look at tangent theta, I'm going to be looking at what a composition functions. So outside function is tangent, the inside function is the theta functions right here. So when I take derivative of tangent, that gives me secant square theta, and times with derivative of the inside function theta, which is going to become d theta dt, which is something that we are looking for, equal to, now when I take derivative of respect to the time for the height, that will be 3,000, 1 over 3,000 times with dh over dt. Solving this for what we need, which is d theta dt, that will help us to get 1 over 3,000 times with secant squared theta, because you're dividing both sides by secant squared theta, and times d theta, dh dt. So continuing this, what are we looking for? We are looking for d theta dt at when the height is 4,000 feet. So with this, at 4,000 feet, right, I know that the value of the dt, the rate of change in height respect to the time at 4,000 feet height is 800 feet per second. So I have no problem getting this answer quickly. But however, we are missing what? Secant squared theta, this value. So to find out the secant squared theta, so whenever we have along the way when we're working on it, whenever we have a missing value, we can always go back to the left-hand side column and then find out or manipulate something that we need, right? So now I can say that now I can look at this picture now, okay, this way. So the way that we're going to look at now is this. Hey, now that I have a fixed portion now, this is 3,000 and this is 4,000 now, because we are talking about a particular height at this point. And we need to know what is my z at this point, right? The hypotenuse, so that I can talk about this angle theta in terms of the ratio of the right triangle. So we know that this is 3, 4, 5 triangle. So, or you can use like Pythagorean theorem to like find it out. And from your trig class, probably you learn those like Pythagorean triplets, right? A few of them you memorize it. So this is basically 3, 4, 5. So therefore, I can basically think of as a 3,000 square plus 4,000 square equal to z square. So therefore, my z is equal to 5,000. Okay, so that's 3, 4, 5 triangle idea, the ratio. So now that I have the z value, I can basically talk about secant theta. So my secant theta, that is basically what? Hypotenuse over adjacent, which is 5,000 over 3,000. So now I can basically plug it in right here. 5,000 over 3,000 square. Any questions before I move on from here? So finally, when I put into the calculator or by hand, when you're computing this, right, you will be getting this result, which is 112 over 125, right? After you simplify everything by hand or calculator, this is what you're going to get. Since this is theta, right, the rate of change in angle, and we will be talking about this is going to be what? In radian per second. That's what it's changing. So finally, I can make my interpretations on this, right? We will be saying that, the camera elevations angle must be changing 12 over 125, or you can put it into decimal number, radian per second, right? To keep the rockets in sight at 4,000 feet up. So that will be the interpretations of this final answer. Any questions before I move on to the next example? So the third example, a 5-foot ladder leaning against the wall, slipping so that its base is moves away from the wall at a rate of 2 feet per second, and how fast the top of the ladder be moving down the wall when the base is 4 feet from the wall. So here's the wall, and here's my ladder. And I know that the fixed number right here is the ladder. The ladder, the length is never changing. So that will be my part. And then when the ladder, right, slip away from the wall, so that means this is slipping into this directions. And therefore, the top part is also slipping down. Okay. So that basically tells me this length right here, right, is going to be changing. So therefore, I will put this length as x. That will be a variable. And because of the top of the ladder is also like, falling down, so the height is going to be changing also. So I will say that this will be what? My y. So that's how I decided which part of the picture will be variable and which part of the picture is not. And the given right here is this. It is telling you that it's slipping away from the wall, right? Move away from the wall at the rate of 2 feet per second. So that means I have dx dt, which is equal to 2 feet per second. And what we are interested in is how fast the top of the ladder is moving down. So we are interested in looking at dy dt, right? At what? When the base is 4 feet from the wall. So we are not talking about every, in general, we want a specific rate of change at the point. So this will become when x is equal to 4 feet. And that's what we want to look for. So now, knowing this, to relate these two variables, right, or to relate these two rate of change, we are looking at the equations using the Pythagorean theorem, which is x squared plus y squared is equal to 5 squared. Is there any questions before I move any further? So to relate, these two rate of change that we have, I'm going to take derivative respect to the time on the left-hand side, and also taking derivative respect to the time on the right-hand side. So this will give me my right-hand side is 0. And on my left-hand side, taking derivative of x squared, remember, x is a function of time and a y is a function of time that we are talking about. So I need to use the chain rule right here. This will become 2x times with dx dt plus 2y times with dy dt. So if I solve for this, right? So first I subtract both sides by this, 2x dx dt. And then when I divide it by 2y on both sides, and this is what I will get. Okay? So when you simplify a little bit, this will become dy dt is equal to negative x over y times with dx dt. And what we want to find out is we want to find out the rate of change of y respect to the time when the base is 4 feet away from the wall. So that tells me I have 4 on the top times with, I know the rate of change of the base moving away from the wall, which is 2 feet per second. Now what I don't know is what is my y. So as in previous example, we're going to go back to our picture and then talk about the instantaneous case. So which instant that we are looking at? When the base is what? 4 feet away from the wall. And my ladder hypotenuse is always 5. So what is my y? So once again, this will be 4 squared plus y squared equal to 5 squared, which is 3, 4, 5, triangle again. So therefore my y is 3. So therefore I can put it right here, 3. So if I simplify this, that will give me dy over dt, right? Derivative of y respect to the time at when x is equal to 4, this will be negative 8 over 3 feet per second. So finally, we want to interpret this. Now, what is this negative talking about? That is basically talking about how fast the top of the ladder is like moving down on the wall. So now the interpretation will be the top of ladder is moving down at 8 over 3 feet per second when the base is 4 feet from the wall. So this last part is important because this instantaneous rate of change is happening at 4 feet, not at 3 feet, not at 2 feet. So you need to indicate it to interpret it clearly. Okay. Any questions before I move any further? So example 4, a car A is traveling west at 50 miles per hour and car B is traveling north at 60 miles per hour. So those are constant speed that we're talking about right here, right? And both of them are headed toward an intersection of 2 roads. So at what rate the cars approaches each other when the car A is 0.3 miles and car B is 0.4 miles from the intersection. So this is how the picture is going to look like. So here's my car A. It is traveling west. So here's car A going this directions, right? And here's my car B and going north. And car A and car B is going to that direction. So that basically this is the intersections of 2 roads right here. So that basically tells me this distance from intersection to car A is always changing. So I'll put X. And the distance from B to the intersection is always changing. So I'll put Y. And also what is changing is because of as they move closer and closer to intersections from both directions, this dotted blue line, which is how far these 2 cars apart directly, they are also changing. So this is my another variable C. And this is basically, we are looking at a right triangle right here. Okay. So now, continuing putting into all the informations, and we know that the rate of change on a horizontal direction, dx dt, right? Since this is a constant speed, it will be what? 50 miles per hour. And we also know that I should more emphasize this because of these are going toward the intersections is a negative. right, directions, and also dy dt, right, when they are moving towards, right, the intersections, the distance is getting smaller and smaller, so it's going to be negative 60 miles per hour. And what we are interested in is looking at what is dz dt, the rate of change between two cars, okay, at particularly when x is equal to 0.3 miles away and then y is equal to 0.4 miles away. And this is what we want to evaluate. Okay. So since this is the right triangle, again, I can use Pythagorean theorem, which is going to be x squared plus y squared is equal to z squared. So before I move any further, are we all okay with this? Do we have any questions? So now I'm going to be taking derivative respect to the time of the equations on the left-hand side and the right-hand side so that we can relate, right, the rate of change that we know to find out the rate of change that we want. So when I take derivative respect to the time on the left-hand side, that will become 2x times with dx dt using the chain rule plus 2y times with dy dt using the chain rule. And remember, at this point, x is a function of time, and then y is a function of time, and then z is also a function of time that we are talking about. Okay? So that will become 2z dz dt. So dividing everything by 2, that will give me x dx dt plus y dy dt. And then finally, I divide it by z on both sides, right? And perfectly okay to do that because z will never be z. We're not talking about 0 yet, right? So that will become 1 over c. So that's the expression that we got. So what we are interested in is we are interested in evaluating, right, this rate of change at when x is equal to 0.3 distance and y is equal to 0.4 miles. So therefore, this will give me 1 over, we don't know the z value, that's what we need to find out, times with 0.3 times with the rate of change in the horizontal directions, that is negative 50 miles per hour, plus 0.4 times with the rate of change in the vertical directions, right, toward that intersection point, which is going to be negative 60 miles per hour. And now we're going to find out the z like before, right? At this instant, what is happening? That's why we want to look at it. So we're drawing a little bit on our picture. My x is 0.3, my y is 0.4, and this is my z, right, at that instance. So using the Pythagorean theorem, 0.3 squared plus 0.4 squared is equal to z squared. So again, this is 3, 4, 5 triangle. For the example purpose, I'm using like, a good number, but when you run into like homework problem, these number may be messy, okay? So it'll be 0.5 right here. So my z is 0.5, so therefore it'll be 0.5. And now, using your calculator and computing this, that'll give me negative 78, okay? And this is basically talking about miles per hour. So what is the interpretation for this value? We are talking about the car A and car B are approaching toward each other, right? at the rate of 78 miles per hour. So it is approaching toward each other, right? Approaching each other. That basically talk about what? Negative portion of it, right? Any questions before I move to the next example? And suppose that a liquid is to be cleared by a cement by pouring it through the cone-shaped filter. And assume that the height of the cone is 16 inches and the radius at the base of the cone is 4 inches. If the liquid is flowing out of the cone at the constant rate of 2 inches cubed per minute, how fast is the depth of the liquids decreasing when the level is 8 inches deep? So, in this case, here is a cone that I have. Okay. And we know that the height of the cone, that is the 16 inches. And the base of the cone, the radius is 4 inches. That's given to you. Now, the question is asking, when the liquid is coming out at the rate of 2 inches cubed per minute, how fast the depth of the liquids is decreasing. So that's basically saying that, hey, here's the height, right? And this height, 16 feet, is always going to be changing since the liquid is pouring out. But what we are interested in is at a depth of 8 feet height, 8 inches deep, and what is how fast the liquid is, like, how fast the depth of the liquid is decreasing. So we are talking about right here, okay, at this level, and my radius will be always changing also at this point, and my height is also changing, right? From the 16 feet is always going to be changing, because as the water level go down, notice that the radius of the cone at the base and at this point is different now, it's smaller. So the radius is also changing. So now what we have is this information. We know that the volume, the rate of change in the volume, because it's talking about in inches cubed, is a constant. So at any time, this never change, right? So the rate of change in the volume is this. Now, what we are looking for and what we are interested in is how fast the depth, right, of the liquids is changing when it is 8 inches deep. That's a question mark right there. Okay? So that's what we are looking for. So since we are looking at the rate of change in volume is given as to find out the rate of change in the height, so we need to use, the related formula for those two, which is the volume of a cone formula. The volume of a cone is 1/3, right, pi r squared h. Now, is there any questions before I move any further? To talk about the rate of change, right, of the height using the rate of change of the volume. I'm going to take derivative respect to the time on both sides. So that will be 1 pi over 3 dt r times h. So if I do this, and the problem is I will have, okay, right here, you need to use the product rule. And also what's going to come out is, because remember that r is a function of time and h is a function of time and the volume is a function of time that we are talking about right here. This is how we are looking at it, right? The change in the volume. So what's going to happen is when I take derivative right here, I will have dr dt, which I don't have that information at all in this given. So therefore, just taking derivative right away like this is not a good idea. Okay? So now what I want to do is I want to rewrite such in a way that this equations will have, or will not have to use this dr dt, right? So how do we figure that out, right? So I'm trying to point out what is the problematic that we're going to be getting if we take derivative like as given, right, into the formula. So now I want to, on the right hand side, I want to rewrite, right, this r in terms of h. So to do that, this is what we need to look at it. We can look at it, this picture that I draw, this portion right here, as a similar triangle idea that we learned before. This entire height is 16, and at some height right here, and that will be respect to, that will be associated with this radius, which we don't know at all, right? That's vary. And then I can look at it as what? The base of the radius, the base of the cone have the radius 4. So this is basically a similar triangle that we can write down the ratio, which is, right, h over 16, that is equal to r over 4. So therefore, I can multiply both sides by 4 to relate it. H over 4 is equal to r. Any questions before I move any further from here? This will become v is equal to 1/3 pi times, replacing r with h to over 4 to the second power times h. Simplifying a little bit, that will become, this is equal to pi over 4 squared is 16, 16 times 3, 48, and h to the second power times h is h to the third power. Now, taking derivative on both sides, respect to the time, that give me dv dt, that is equal to pi over 48 times with 3h squared times with dh dt. So we can get what we want to look for. So solving for dh dt, right? So this will give me I can reduce 3 and then 48, which will give me 16. And when I multiply both sides by reciprocal, right, of this, that will become 16 over pi h squared times with the dv dt. So now what we want is we want to evaluate at a specific height, right? And what is the instantaneous, what is the rate of change of the depth it's going to be. So I want to find out dh dt at specifically when the height is equal to 8 inches deep. So which is equal to 16 over pi times 8 to the second power times with my rate of change in the volume is 2. So what's going to happen right here is when I compute this, that will give you 64, right? 8 times 8 is 64. So 16 golden 64 4 times, and then reduce it with 2. That will give you 1 over 2 pi. Are we all okay with this? So now, notice that in this problem, I'm not sure you guys thought about this or not. In the beginning, I never put a negative sign when I mentioned about the volume is a decreasing at, right? Or the volume is like, leaking out, flowing out at the rate of 2 inches cubed per minute. I never indicate that with the negative sign. So what happened is when I got my results at the end, notice that I got a positive value, 1 over 2 pi. So if you are not paying attention to this, like, are you talking about this is like, the increase in the depth of the water level, the liquid level, right? So you really have to be careful on that part. If you don't put, all right, a proper symbol or proper signs in the given informations, then you really need to know how to interpret it correctly and explain it back to whoever looking at your work. Okay. So that's why like you have to be careful with this. So in this case, even though I don't have a negative sign right there, but we know that the rate of change in the volume is like, putting the liquid is flowing out. So therefore, the depth of the depth of the height is also the depth of the liquid is also decreasing. So I would say that in this case, the rate, right, of the depth of liquids is decreasing at 1 over 1 over 2 pi inches per minute when the level is 8 inches deep. And this will be my final conclusions. Is there any other? So example 6, an air is being pumped into a balloon, right? A spherical. So the volume increases at the rate of 100 centimeter cubed per second. Now it's asking how fast the radius of the balloon is increasing when the diameter is 50 centimeter. So that basically tells me here's my sphere, and the sphere is like this, and then we are talking about here's the radius. That's always changing, right? As the time move on. So the given is the volume, right, of this sphere is changing, increasing at a speed of 100 centimeter cube per second. Now the question is asking you how fast the radius is changing, right? How fast the radius is increasing when the diameter is 50. So when the diameter is 50, that means my radius is what? 25. So that's what we want to evaluate at that point, what is happening. So to relate this increase the rate of change in the volume to the rate of change in the radius, we have to use the volume formula for the sphere. Volume is equal to 4/3 pi r cubed. So you need to remember and recall all the basics formula for, volume, area, surface area, some of them, okay? So now if I take derivatives respect to the time on this, so it'll be dv dt, which is equal to 4/3 pi times 3r squared dr dt using the chain rule. So this will give me dv dt is equal to 4 pi r squared times dr dt. And you may evaluate this at when the radius is equal to 25 by substituting it. And that will give you your final result. And don't forget to interpret it. So example 8 is talking about a man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate the searchlight's rotating when the man is 15 feet from the points on the path closest to the searchlight? So here's a straight path, and a man is walking. Right? A person is walking, and it is talking about there is a searchlight, right, that is located 20 feet on the ground, 20 feet from the path. So here is a searchlight, and this is 20 feet from the ground, from the straight path. And it's already telling you that this distance, okay, from the path, walking path to the searchlight, the closest distance is 20. Yeah. Now it's asking you if the man is like, walking away, right? And then 15 feet, so which is up to this point, maybe. So this distance is going to be changing all the time, right? If you're moving this directions. So that distance is changing all the time. So I would say that this will be my x right here. So what we are interested in is, since this searchlight is focused on a man, on this man, right, this person. So as the man moves, this searchlight will also rotate. So what happened is, one is at 15 feet, and we are talking about what is the angle of rotation, what is how fast this angle is rotating. So right here, it's giving to you that dx dt, right? The speed of the man walking on average is what? 4 feet per second. That's a constant speed. And we want to find out what is the rate of change in the rotations of the searchlights respect to the time when this man is basically 15 feet from the point where the closest to the searchlight, which is this part right here. Okay? So we already know that this searchlight to the path, the closest is what? 20 feet. Awesome. So that's what we are looking for. So looking at this, basically, we are talking about a trigonometric functions again. Tangent theta, that will become opposite over adjacent, which is 20, because we don't want to use sine or cosine, right? Because we don't know this hypotenuse right here, and we don't know the rate of change on this hypotenuse right here. So when I take the derivatives on both sides, that will be secant squared theta times with the theta dt, that is equal to 1 over 20 times with dx dt. Again, simplifying a little bit, that will become d theta dt, that is equal to 1 over 20 times secant squared theta dx dt. So what we are interested in is looking for the theta dt at when x is equal to 15. So the easy part is we can plug in all the value, but however, we need to know how to find out the secant square. So therefore, we need to go back to the picture and then talk about that instantaneous case, which is this angle theta, right? It's happening on one is 20 and then this is 15. So I need to find out what is this value so that I will be able to, use the ratio to find out the secant theta. So 20 squared plus 15 squared, that must be equal to z squared, let's say that. So therefore, what is my z? And once you got that, you can basically have all the information to finish up this example. Is there any other questions before we move?